Dear students, welcome to the next lecture in this course on signals and systems. So, in the last unit, we discussed the number of basic system properties, and of these various basic properties, two of the properties, if you remember, were the linearity and time invariance. Okay, now these two properties they play a fundamental role in the signal and system analysis because of the many physical phenomena that can be modeled by the linear time invariant systems. So I already told you that whenever a system possesses both these properties, then we call that system as linear time invariant system, or in short we can also call it as LTI system. Okay, so linear time invariant system, in brief it is called a LTI system. Okay, now if we can represent the input to an LTI system in terms of a linear combination of a set of basic signals, then we can use superposition to calculate the output of the system in terms of its response to these basic signals, isn't it? Now a main problem in the system analysis is determining the output response to some specified input. Although this can be answered in many different ways. One way is to solve the differential equation describing the system and given the specified input and the initial conditions. So this we had already seen in the last lectures, that how to solve the differential equations to obtain the output of any system. Now in the coming lectures we will focus on another second method that actually use the linearity and time invariance of the system. Okay, so for that we first have to discuss the impulse response. Okay, so impulse response is nothing but it's the output of an LTI system due to a unit impulse signal input applied at time t equals to 0. Okay, let me just show it with the help of a figure. Now let's suppose that this is an LTI system. Okay, this is its input and its input is a impulse signal. So you are already familiar with the impulse signal, we have already discussed it in the first unit. So in this case the output which you will get is called the impulse response of the system. So impulse response is defined as the output of an LTI system due to a unit impulse signal input applied at time t equals to 0. Okay, so this ht will be called as the impulse response. Okay, so you can also represent it in this way, that if the output to any input xt is yt, then if the input is an impulse signal, then the output will be called as impulse response, and we denote the impulse response with this symbol ht. Okay, so this will be called the unit impulse response of this continuous time system, and this is the unit impulse function applied as an input. So this was for the continuous time system, this was for obviously continuous time system. Same thing you can have for discrete time system as well. Okay, so for discrete time system, let's suppose the input is xn, output is described by yn. So if the input is this delta n, then the impulse response will be hn. Okay, so this is for discrete time system. So if we are given the impulse response of a system, we can determine the output due to an arbitrary input signal by expressing the input as a weighted superposition of time shifted impulses. Okay, so for linearity and time invariance, the output signal must be a weighted superposition of time shifted impulses. So this weighted superposition, actually it is called the convolution sum. Okay, convolution sum for discrete time system and it is called the convolution integral for continuous time system. Okay, so these are two different things. For discrete time system, the that term is defined as convolution sum, whereas for continuous time system we generally talk about the convolution integral. Okay, so now we try to have an expression of the convolution integral. Okay, now you generally know that the linear systems, they are governed by the superposition principle. So let us suppose that if there are two inputs x1t and x2t and their output is represented by this y1 and y2 respectively, so the system is linear if the response to the input xt equals to a x1t plus b x2t should be equal to a y1t plus b y2t. Okay, so this is what we have discussed in linearity property when we were discussing it in the first unit. And more generally, if the input xt is the weighted sum of any set of signals xit, if the response to let's suppose that if the response to this signal xit is denoted by this yit, okay, and if the system is linear, then obviously the output yt will be the weighted sum of the responses yit. Okay, so this is the condition of linearity. Okay, let me just write it down in the expression form. Let's suppose that the input is represented in this way: a1 x1t plus a2 x2t and plus so on an x and t. Okay, so this can also be represented in this way, that just summation ai xi t, where I equals to 1 to n. Okay, so if the input is represented in this form, so for the system to follow the linearity, or for the system to be linear, the output should be a1 y1 t plus a2 y2 t plus so on an yn t, isn't it? So it can also be represented in this form, I equals to 1 to n and ai yi t. Okay, so this is the basic you can say meaning of linearity property, which we have discussed in the unit first. Okay, and we have also discussed the shifting property of the impulse function. So if you just recall that the shifting property of this impulse function, which we discussed in the first unit, was something like this. Okay, x minus infinity to infinity x tau del t minus tau d tau. So it actually shows that any signal xt, it can be expressed in terms of the weighted impulses. Any signal xt can be expressed as a continuum of weighted impulses, isn't it? So it means that it can just be represented in terms of this weighted impulses. Okay, now consider a continuous time LTI system with an input xt. So using the superposition and the time invariant property of the LTI systems, we can express the output yt as the linear combination of the responses of the system to shifted impulse signals. So if xt have an output yt, and then the impulse signal have an output which is represented by ht, that is its impulse response. Okay, so now if the input becomes a shifted version of the impulse signal, then because the system is linear and time invariant, so the output will also be shifted. And if the input is now represented in this form, that is in terms of weighted impulses, then the output should be of this form. So this can be written in this form, that if your input, which is represented by xt, okay, so if your input is in the terms of weighted impulses, then for the system to be linear and time invariant, what should be the output? The output should be evaluated in this manner, where this ht minus tau will be the impulse response. Now what you see from here, that we obtain the system output yt due to an arbitrary input xt in terms of the unit impulse response ht. Okay, so the output have this term of impulse response. So output is actually in the form of, you can say, is expressed in terms of the impulse response. Okay, So this formula or this expression actually, let me just cover it in a box. This expression will be called the convolution integral. This is the, you can say, the output, and it is generally called the convolution integral of xt and ht. Okay, so I should write it down on a separate page maybe. So if you have been given two signals, maybe xt and ht, okay, so convolution of xt and ht is expressed by this symbol. Okay, so xt and this symbol which is looking like a star, so this is actually the symbol of convolution. So if there is a symbol like this in between two signals, then this means that there is a convolution operation which have to be performed in between these two signals. Okay, so this is actually the symbol of convolution, you can say. So the convolution, if it is represented by this yt, so the convolution of xt and ht will be equal to okay, so this is another way of calculating the output of an LTI system. So here we have used the properties of linearity and time invariance in order to calculate the output. Okay, now we will see a numerical problem based on this convolution. Let us suppose that you have to find the convolution of two continuous time signals which are given as ft equals to 3 cos 2t and gt is given as e raised to the power mod t, which is equal to e raised to the power t for t less than 0 and e raised to the power minus t for t greater than equal to 0. Okay, so the question was to find the convolution of these two signals ft and gt. Okay, so just by the definition which we have developed for convolution, yt, which is convolution of ft and gt, will be represented in this way. Okay, and this will be nothing but the expression of convolution you have to put f tau g t minus tau d tau. Okay, now if you just represent f tau, that is just replace this variable t with tau, so f tau is 3 cos 2 tau and gt minus tau can be obtained just from gt, So it can be written as e raised to the power t minus tau, and this is for t minus tau less than 0, or it can be written in terms of tau greater than t. And the second one will be e raised to the power minus of t minus tau for t minus tau greater than equal to 0. That means for tau less than equal to t. Okay, so just you write down the expression for convolution and put the limits. Obviously the integral will be divided into two parts because gt is defined as differently for the two different parts. Okay, and the second part will be from t to infinite. Now just this will reduce to a simple integral problem. You have to solve it. Okay, so you can solve it in different manners. I will just write the solution for it. Okay, so next I think you should solve it. The final answer should come as 6 by 5 cos 2t for all the values of t. So this should be the final result of the convolution operation between the two signals. Okay, so in this way in this lecture we have just introduced or started a second method for solving the, you can say, the output of the signals systems, sorry, and this is called convolution. So you have seen that in calculating the convolution we have utilized the property of the linearity and the time invariance of the system. There are many more problems to be solved, and which we will solve in the coming lectures. So this is all for today. With this much we stop, and will solve some more problems in the coming lecture. Thank you very much.